So let's sketch the derivation of the three main results of the CAPM. The first is that the expected risk premium is equal to the expected market risk premium times this proportion coefficient. The proportion coefficient is a function of the correlation and the relative risk, and the market risk premium is a function of the average level of risk aversion of all the market participants times the expected risk of the market. So first, we just have to do a quick definition, and you may have seen this before in a previous statistics class. We'll demonstrate it later on, but it's that the beta in any regression equation is equal to the covariance between, in this case, the stock and the market divided by the market's variance. And that's just sort of a definition. This is the computation that Excel is doing when it spits out this beta. Okay, so let's talk about our first relationship here. And again, this is many, many pages in the textbook. We're really gonna just sort of skip this and sketch it out. But here's my first relationship that I wanna sort of demonstrate, that the risk premium for some stock I is equal to the risk premium of the market times this beta. And so we have to make an assumption. And the assumption, and this goes back to our idea of sort of efficient markets and rational behavior, is that in equilibrium, all risk-reward ratios are equal. And if this is true, if it's equal for individual stocks, then it must be true for the aggregate of all stocks. It must be true of the market. And so if it's the case that the risk premium for stock 1 divided by its covariance with the market is equal to the risk premium for stock 2 divided by its covariance with the market, and then this is true for all stocks relative to the market, so stock N relative to the market, it must be true for the market relative to the market, and therefore true for this. So in equilibrium, the risk premium for stock 1 divided by its correlation with the market must be equal to the risk premium of the market times this market variance. What if they're not? What if this first term is worth more, is bigger than this last term? Well, then stock 1 is attractive. It's earning more than it should relative to its risk. And so what happens is people buy the stock, the price goes up, the return goes down until they are equal. And so in equilibrium, it should be the case that the return of stock 1 relative to the risk-free divided by its covariance with the market is going to equal the market's risk premium divided by its variance. And again, we're skipping a lot of math here. But what I can then show is if I move this to this side, the covariance with the market divided by the variance with the market, I get that this is equal to beta, and I've derived this first relationship. And again, we've really sketched this. We haven't proven it, but what we're saying is that a stock's return is proportional to the market risk premium. And the proportionality coefficient is that beta. So according to the CAPM, all you get is market risk premium times beta. There's nothing else on here. Let's look at the second result, and that is that the beta, this coefficient, this proportionality coefficient, is equal to the correlation times the ratio of the volatilities, the standard deviations. So let's consider a stock I. Its return can be described by, or essentially decomposed into, the following. The return of some stock can essentially be the alpha plus the beta times the return of the market plus the error term. So for any given return, I can get to this dot on the chart by going to the alpha, taking the return of the market, multiplying it by the beta. That's going to get me to some spot on the line, and I get the rest of the way there by adding or subtracting the error term. And so since this describes the return of the stock, I can substitute this for the return of the stock. So next what I want to do is I want to compute the covariance of the return of the stock, return of stock I with the return of the market. And then I'm going to sub for Ri using the above. So here is the covariance of the return of stock I and the return of the market, and all I'm going to do is I'm going to substitute in for the return of the market, the return of stock I in this equation. The next thing I'm going to do is going to sort of distribute the covariance. the covariance of this equation with the return of the market is going to be equal to the covariance of the market with alpha, the covariance of the market with beta RM, and the covariance of the market with the error term. And so these are my three distributed terms. And I can see that I have the blue term in each, and I have the yellow highlighted terms, a portion of the yellow highlighted term in each. And so now I want to think about these three separate terms. The first term with the blue letters is the covariance of alpha versus RM. And what this is the covariance of a constant which never changes and the return of the market. And so the return of the market, its covariance with something that never changes is 0 because this never changes. And so this term goes to 0. And the covariance of some random variable that's completely uncorrelated with the market is also going to have a correlation or a covariance of 0. So the way to think about this is the return of the market and how it covaries with your street address. And your street address is fixed, it never changes. And so therefore, the covariance of the market and your street address is 0. And this is the covariance between the market and something that's completely unrelated. So for example, lottery numbers, right? If you're going to look at the pick 3 number, sometimes the pick 3 number is really, really high. Sometimes it's really, really low. Sometimes the return of the market is high and sometimes the return of the market is low, but they are uncorrelated. And so this first term and this third term both drop out. And so that I get the covariance of the stock relative to the market, the covariance of the stock relative to the market is just equal to this beta term times the return of the market, times the return of the market and its covariance with the return of the market. And I can write this way. I can pull the beta out. This gives me the covariance of the market with itself, which I can then rewrite as the variance. And so that I get the covariance is equal to the beta times the variance, solve for the beta by pulling that over. And I know by definition that the correlation times the ratio of the standard deviations is equal to the beta. Okay, so what makes beta bigger? Well, greater correlation makes beta bigger, and the ratio of standard deviations, if it's the case that the stock is very volatile relative to the market, then I have a larger beta.